All right, class, in this lesson we're going to take a look at the real number system, which is just expanding from our rational numbers, the first four sets of natural, whole, and integers, and it's including those that are not rational or irrational numbers. Now, we've got rational numbers that can be represented as fractions, as we looked at in the last lesson, with decimal parts that repeat forever or terminates, and so that means that irrational numbers are all the ones that are not rational, meaning not rational. So they have a decimal part, of course, that does go on forever, but it doesn't repeat. So it does not repeat, but goes on forever. So examples you've seen before would be pi. Pi is irrational. These numbers here, it just looks like it repeats 5.12, but then the one part keeps expanding. So there's a pattern to it, but it doesn't repeat. And then the square root of 2, if you actually take that on your calculator, it'll go on forever but not repeat. This number right here is the golden ratio. If you've been into art, I'm sure you've seen that number before. And then E is 2.7182. That's a number that we'll see very often in math. So these are all examples of irrational numbers. So number that is in this form here with the square root is called a radical, and the symbol is called a radical sign, and x is called the radicand. So we've seen radicals before. I use for me to call it square roots, and I'll be probably calling it square roots here because these are all square roots in particular. The reason why it's saying square root is because they have a 2 in front of the root that's not written there. But this also works with other roots, not just square. It works with the third root, fourth root, and we'll see examples of those later. So demonstrating equivalence is that what I can do here is break up these into individual parts where I can rewrite this as, I can rewrite this to be the square root of 6 times the square root of 5. So if you take your calculator and do square root of 30, that would be equal to taking the square root of 6 and multiplying by the square root of 5. So if you actually take your calculator and do this, you would get those two exact answers. And the same thing happens over here. If I take the square root of 7 and divide it by the square root of 15, it would be the same thing as saying the square root of 7 divided by 15. So the point here being that if you actually use your calculator on these, you will get the same exact decimal, and it just demonstrates that this rule is in fact true. So, that just disappeared. That's great. Here we go. So, simplifying radicals using prime roots is more interesting than using your calculator to me. But if we take 15 and square root of 5, what we can do is take a look at multiplying them. And what we'll see here is that when I multiply square roots, it's the same using the rule we just had on the last slide. I can rewrite this to be the square root of 15 times 5. And that's what you want to do is when they have the same root, in other words, they're both square roots like this. This first I'm actually writing 2, but they all have an imaginary 2, which is saying what squared gives you 15, what squared gives you 5. We don't know, so we left it. Is you can rewrite it to be the square root of 15 times 5. So then if I actually multiply that out, 15 times 5, then what I can do is rewrite it to be 15 broken down to be 3 times 5 times 5. And rather than actually multiplying it together and getting bigger and writing the square root of 75, I can rewrite this to be the prime roots here. 15 breaks down to be 3 and 5. The reason why I'm doing this is because now I can reorder the product. I can actually reorder the product to be the square root of 3 times the square root of 25. So hopefully you see what I did there is I just broke down my prime factors. This 3 times 5 is still 15, but if I rearrange it, I can make the 5 times the 5 be square root of 25. Now what I just did was very useful because the square root of 25 is 5 times the square root of 3. So this whole thing can turn out to be 5 times the square root of 3. So let's try this again, see if we can make it become clear. Keep losing my PowerPoint, apparently. There we go. So we can do this with division also and rewrite it to be the square root of 54 over 12, which we can actually reduce to be 2 and times 27 over 2 times 6. And we can actually reduce that further to be 2 times 3 times 9 over 2 times 3 times 2. And what's nice is that I can actually cancel out my 2's and cancel out my 3's, and what I'm left with is the square root of 9 over 2. And then here this is going to turn out to be the square root of 9 divided by the square root of 2, and that's going to turn out to be the square root of 3, or sorry, the square root of 3 over the square root of 2. Now we're going to learn how to rationalize the denominator in the next slide. It's actually my next example. But what I can do here is, rather than rationalize this, we'll talk about why this is what needs to happen here. But what I could have actually done up here was a little bit different strategies. I could have rewritten this to be the square root of, if I combine these, to be 6 times 9 over 4 times 3. What I could have done then would have turned into, oops, sorry. Yeah, no, that's right. Is turned it into the square root of 9 over square root of 4 times the square root of 6 over 3. See how I rearranged it? I put the 9 in front and the 4 in front, and then I put the 3 behind and the 6 behind. So I'm just I can break it up into individual parts of the roots, and so that this will turn out to be 3 over 2 times the square root of 2. So it's actually the equivalent answer to what we just did there. So it's just rearranging my roots to be whatever I want them to be, so that I can actually pull out nice square root portions, like the square root of 9 is 3, the square root of 4 is 2. And so that's looking at it up here. It's combining these 2's together, so that way I could have pulled it out and not had a irrational portion on the bottom. But the answer that I had over here was sufficient, and what we'll learn on the next slide is how to rationalize the denominator. So let's talk about that. Rationalizing denominators especially needs to happen when you've got a square root on the bottom like this one, and there's no nice canceling and manipulating of the actual fraction itself on the inside to make it so that I can square root in a way that I won't have a irrational portion. So what happens here is you can just multiply the top and the bottom by a square root of 12. And what happens is I can rewrite this to be 7 square root of 12 over the square root of 144. Because my 12 times my 12 gives me 144. And that allows me to have 7 square root of 12 over 12. Because the square root of 144 is a nice actual square root, turns into 12. So this is rationalizing denominator. So this is an irrational number, irrational. And so what we did was we rationalized it. We made it rational. It actually has no square root down there, so it is actually a rational number. Okay, so we'll have application problems in our assignment where we have to rationalize denominators. Okay, so here we're going to add, and then we'll eventually subtract irrational numbers. They have radicals. The only way that you can add radicals is if they have the same root part. In other words, I can't add these the way that they are. It has to be, in other words, it's like 5x's plus 8y's right now. I can't add unlike terms. They have to be like terms. So what I can do is erase what I just wrote and turn it into, I can make it so that they actually do have the same root left over. If I take a look at this 12 and rewrite it in its prime factors, this turns out to be 2 times 6, which is 2 times 2 times 3. So this is the prime factors of 12. If I actually write them out, 2 times 2 times 3 multiplies to be 12. And what I like here is that the 2 times the 2 is actually 4. So this is really square root of 4 times the square root of 3. Square root of 4 is just a 2. So that means this 8 is still here. So it's really 8 times 2 times square root of 3. So this is actually, if I continue to rewrite it, is 16 square root of 3. So what I'm actually adding here is not 5 square root of 3 plus 8 square root of 12. It's really 5 square root of 3 plus 16 more square roots of 3. So in all, I have 21 square roots of 3. I hope you're hearing how I'm saying that, is that the 5 and the 16 add together to make my 21, because this is 5 square roots of 3 and another 16 square roots of 3 to make a total of 21 square roots of 3. Yep, 21 of them in total. So this always works when you can have prime factors that actually end up with the same square root at the end. But sometimes, like on this problem, it's not going to work out. Because if I write this as a prime factorization, this is going to be 3 times 3 times 5. Because 3 times 3 is 9, 9 times 5 is 45. And this square root is going to turn out to be 2 times 3 times 2, which gives me my 6 times 2. And then if I actually prime factorizate, or actually square root this, this is the square root of 9 times 5, square root of 5, plus the square root of 4 times square root of 3. And this turns out to be 3 square root of 5 plus 2 square root of 3. So we've done a great job of prime factorization on this, but it does not allow me to add in the end. So let's go ahead and take a look at subtraction now. PowerPoint's not liking that. I'm switching back and forth here. Oops. Yes, I don't have subtraction. Sorry. We've got properties. Subtraction works the same here, though, where in the end I can just subtract the quantities rather than add them. Here we go. So we've got our properties here. If you want to take a look at those, might be something to take a snapshot of so that you can identify them later. The biggest one that you're going to worry about is the distributive property. That is not, yes, it's the last one there. So down here, oops, there we go. Down here, the distributive property is showing you that if you take your parentheses, you would multiply your A times your B and your A times your C. This is the one that just comes up most often, but inverse operations is here, additive identity, multiplicative identity. So additive identity has 0 to it, multiplicative. So basically, you're trying to figure out what would you add that doesn't change it, what would you multiply that doesn't change it. And then we've got the associative property, which regroups a problem. The commutative property rearranges the problem, the order that they go. And closure is just saying, this happened. It's kind of like, well, I just added. It's closed. I just multiplied. It's closed. So it's like a closed statement. For example, A here, these are all examples of what you would be doing in your homework. A is saying I've got 3 plus 4. It's an integer. Okay, so that's just a closed statement. You would add those and that happens, so it's closed. B is saying I rearrange these. So I have square root of 2 plus pi and pi plus square root of 2. So this is commuting. They're moving around. They're commuting. C is I'm adding nothing. I'm changing nothing. It is the identity property for addition. Here we've got D, which is multiplying in parentheses, and then you're not. What you got to be careful. What you got to be careful of is we're not distributing here. What we're doing is we're regrouping. We're saying I can multiply the last 2 and then the first one, or I can multiply the first 2 and the last one. This is the associative property. It's regrouping. Here E is the additive inverse because I'm adding and it results in a 0. And F, this is the multiplicative inverse happening. And last G is our distributive property. So they're mostly in order here, but just some different properties and different connections to what they're actually doing, because you do have some homework asking about that. And then you have an application problem just like this one, where it says the police is investigating an accident, and they use this equation. You'll have the same equation in your assignment. It's just going to be different numbers. To estimate the speed at which a vehicle is traveling when the driver hit the brakes, here V stands for the speed of the vehicle in miles per hour, and L is the length of the skid marks in feet. The car leaves a skid mark of 330 feet. How fast was the car going when the driver hit the brakes? So really all you have to do here is recognize that this is the feet for the skid mark, and so that goes in for L. So your job is to just find B, and we want to leave our answer as a square root, a radical. So we've got 2 square root of 5 times 330. Okay, so what we want to do is simplify this. So I don't actually want to multiply that out. I want to actually break it down to its prime factorization. So if I do that, I got 330 breaks down to 2 and 115. And then if I break it down further, I can divide by 5. So let's check that. So I got 330 divided by 2, 165. I actually did it wrong. I'm sorry. So 330 divided by 2 gives us 165, not 115. And then divide that by 5. I get 33. And then divide that by 11, and I get 3. So this can be rewritten to be 2 times the square root of 5 times, I'm going to put the 5 next to it, times 2 times 11 times 3. So all this amount gave us my 330. And again, the reason why I wrote it that way is so that I can rearrange the 5 to be 2 square root of 25 square root of 2 times 11 times 3. That way I can take this and turn it into a 5. So this actually is a 5. And then 5 times this 2 is going to give me 10. So it's 10 square root of, and then you just want to go ahead and multiply your 22 times 3 to get 66 here. So my V is equal to 10 square root of 66. So what I did was I multiplied my 2 times my 3 and 11 to give me the 66. And I multiplied my 2 times my 5 out in front. So your reduced, simplified answer is 10 square root of 66. And that's it for this section. So if you have any questions, let me know. Ask through the email link in the lab.